Hello, and welcome to today's chemistry class for S.S.1. Our topic today would be empirical and molecular formula. Lesson objectives. At the end of this lesson, the students should be able to define empirical formula, carry out calculations involving empirical formula, explain molecular formula, and carry out simple calculations involving molecular formula. Before we go into the class proper, I would like to tickle your fancy a bit. The most important of my discoveries have been suggested to me by my failures. This was given to us by Humphrey David. I hope you understand. So, let's get started. What is empirical formula? The empirical formula of a chemical compound is the simplest whole number ratio of atoms present in a compound. An empirical formula makes no mention of the arrangement or the number of the atoms in the compound. A good way I can explain this to you is like saying you should look at the S.S.1 block of your school. Maybe you have S.S.1 A, B, and C. Now, empirical formula will only tell you that in S.S.1 A you have 10 students, that is all. In S.S.1 B you have 15 students, or in S.S.1 C you have 20 students. Empirical formula will not bother about the total number of students in S.S.1. It will only bother about the simplest ratio, class by class, tell you this in this class we have this number, in this class we have this number, and that is all. It is molecular formula that will now come and tell you that in the whole of S.S.1 we have so number of students. But empirical formula does not bother about that. It only bothers about the number of students per class, the simplest ratio. A good example, NO, that's nitrogen and oxygen, is the empirical formula for both NO, NO2, and N2O, because it is the simplest whole number ratio for all of them. Their arrangement is not considered here. You see my explanation? Their arrangement is not considered here. Now let's take a look at molecular formula. Like I said in the earlier slide, the molecular formula will tell you the total number of atoms you have in a molecule. It will not bother now about the simple ratio, which is what empirical formula bothers about. The molecular formula, on the other hand, shows the number of each type of atom in a molecule. The structural formula shows the arrangement of the molecule and the exact position of the atoms. It is also possible for different types of compounds to have the same empirical formulas. Now, based on our earlier illustration about the classroom, you will note that if you want to know the total number of students in SS1, you must go and count each class. SS1A, what do we have? SS1B, what do we have? SS1C, what do we have? By the time you get for each of the classes, before you now add it together and get the total. What this means is that before you can know molecular formula, you must be able to know the empirical formula before you can calculate the molecular formula. Let's look at these simple steps that we can use to calculate empirical formula. The first thing you will do is to start by bringing out the percentage or mass composition of the elements in the question. A good example is this one now. In the question, carbon has 85.7%, while hydrogen has 14.3%. It might not always be percentage. Sometimes they will give you in masses. So they will say 85.7 grams and 14.3 grams. But in this our question, they are saying 85.7% and 14.3%. Then the next step is that you will identify the atomic masses of each of the elements. In this case, carbon is always 12, that is the mass of carbon, while hydrogen is always 1. The next step, you are going to divide the percentage or mass composition by the atomic masses of the respective elements. A good example, you can see, if the mass of carbon is 12, we are dividing its percentage composition, that is 85.7 by 12. That will give us 7.14. And then hydrogen is 14.3% divided by its atomic mass. That will give us 14.3 divided by 1, that's 14.3. In the next step, after dividing by their respective atomic masses, you will look for the smallest number in the answer above and use it to divide through all of them. In this case, 7.14 is the smaller number between the answer we got above. So we divide through by 7.14. That will give us 7.14 divided by 7.14, that is 1, and 14.3 divided by 7.14, that is 2. Round off to the nearest whole number and write the number as a subscript beside the element. So the empirical formula in this case will be CH2. Don't forget, in chemistry, that C, we should have said C1H2, but once it is 1, we just don't write it. Let's take a good example. Determine the empirical formula for a compound containing 74.0% carbon, 8.65% hydrogen, and 17.3% nitrogen. Now, take a look at this table. Carbon, we have been told, has 74%. Hydrogen, 8.65%. Nitrogen, 17.3%. Now, to the next column. We divide by their respective masses. Carbon is 12, so we say 74.0 divided by 12. Hydrogen is 1, so 8.65 divided by 1. Nitrogen is 14, so 17.3 divided by 14. To the next column. The answers for each. For carbon, we have 6.16. For hydrogen, 8.56. For nitrogen, 1.24. If you check through these answers, you will see that 1.24 is the smaller number. So we use it to divide through all of them. That is what gives us the answers in the next column. So 6.16 divided by 1.24, that will give us 4.96. 8.56 divided by 1.24, that will give us 6.90. 1.24 divided by 1.24, that would give us 1. Approximating to the nearest whole number, we are going to have, for carbon, 5, for hydrogen, 7, and for nitrogen, 1. That will give the empirical formula of the compound to be C5H7N. Let's now consider how to calculate molecular formula. Remember that the empirical formula repeats itself n number of times to form the molecular formula. Therefore, empirical formula times n will give us molecular formula. E.g., a hydrocarbon with empirical formula of CH2 has a molar mass of 56. Calculate its empirical formula. Remember, I told you, you must know empirical formula first before you can calculate molecular formula. So let's take a look at the solution. Empirical formula times n is equal to molar mass. The empirical formula is CH2 times n, and that will give us 56, which is the molar mass that was given in the question. Now, the mass of carbon is 12, plus hydrogen has a mass of 1, but there are 2 of them. So we now have 2 times 1. Everything is equal to 56. Now, 12 plus 2 in bracket n is equal to 56. 14n, if we open the bracket, is equal to 56. N is equal to 56 divided by 4, and that is 4, which is our answer. Therefore, let's now take a look at how to calculate percentage composition of elements in a compound. The percentage composition of an element in a compound is its total mass divided by the molar mass of the whole compound times 100%. Example: calculate the percentage composition of oxygen in Na2CO3. Solution: mass of oxygen in the compound, 16 times 3, that will be 48. Mass of oxygen is 16 and there are 3 of them, Na2CO3. Now, the mass of the whole compound, that's the Na2CO3. Sodium is 23, there are 2 of them, times 2, plus carbon is 12, and we know that oxygen is 16, times 3 of them. The total will give us 46 plus 12 plus 48, and that gives us 106. The percentage composition of oxygen in Na2CO3 will now be 48, which is the mass of oxygen in that compound, divided by 106 times 100. That will give us a final answer of 45.28%. Let's now take a little summary of what we have done so far. In this class, we have learnt about empirical formula, molecular formula, and then percentage composition of elements. Time now for assessments. Question 1. Calculate the percentage composition of copper in copper sulfate, that is CuSO4. Question 2. Calculate the percentage of oxygen in aluminum sulfate. Question 3. 9.2 gram sample of a compound is 2.8 grams of nitrogen and 6.4 grams of oxygen. Find the empirical formula of the compound. And so with this, dear students, we have come to the end of this class. Thanks for watching and see you in the next class.